When we took the break, I had persuaded one of my colleagues, Professor Akgerman, to report on some work that he is doing. The title of his talk will be Direct Synthesis of Mixed Sulfide Catalysts for Hydrogenitronation. His co-authors are Bedri Bospart, C.P. Jansen, and Professor Marcetta Darensborg in the Department of Chemistry.
Thank you, Ray. What I'll be talking about is direct synthesis of sulfide phase on the catalyst using organic precursors. Some preliminary characterization study on the supported catalyst, as well as some reaction results. My co-authors, Professor Darensborg from chemistry and his student, Mr. Jansen, and Dr. Bospart is working with. Our objective is to synthesize MM prime sulfur type mixed sulfide from an organic precursor and deposit the mixed sulfide on a suitable carrier, preferably alumina in this case, and characterize the catalyst, as well as look into hydrodenitronation activity of the catalyst. And in hydrodenitronation, we're looking at gas phase HDN of quinolene with quite a bit of excess hydrogen. Some of the reactions that are possible are listed here. And basically, I'll be talking about this catalyst except the ammonia salt of it rather than the, tetraethylamine salt. But we have tried also the cobalt molybdenum as well, and that gave some positive results too. These three compounds we have not prepared yet. So I will be basically talking about this compound over here with that group changed to ammonia group, NH4 group. Now, these compounds have been studied for a long time. I'll just give one reference, although there are quite a few other references by Elsner et al. And they prepared this organometallic precursor with the M group being cobalt or nickel, and the other one being molybdenum or tungsten, and performed TGA, DTA, XPS, and XRD studies on characterizing the catalyst as to the mixed sulfide phase. The catalytic activity is tested by using a biphenyl hydrogenation, and the thermal decomposition of the organic results in a mixed sulfide phase. Sulfur is 5 to 7 depending on the decomposition media, whether you use nitrogen or hydrogen-hydrogen sulfide mixture. And between 200 to 300 degrees, there are two endothermic peaks, basically the organic group and hydrogen sulfide coming off. Activity, or at least the initial activity, is higher compared to homogeneous sulfide catalyst or sulfide catalyst prepared by inorganic salts. And the catalyst deactivates similar to these type of catalysts. And the X-ray diffraction indicates a phase separation and appearance of a nickel sulfide and a molybdenum sulfide peaks, whereas initially it's amorphous to the X-ray. We tried to prepare this catalyst and impregnate alumina with it, but these are pretty much unsoluble, or they are not very soluble in anything. We did some work with acetonitrile, but it's very slightly soluble and impregnation becomes tedious. So we synthesize it directly with alumina and precipitate it together. So basically it's alumina synthesis followed by addition of nickel nitrate, followed by addition of the molybdenum sulfide, precipitation, extrusion, and calcine it. And X-ray, IR and color change precipitation indicates that the organic complex is there. Give you an example of the DTA results for the typical alumina we prepared. We have the 1 two peaks there. I guess this is hydroxyl group going into oxyhydro groups, and this is converting into alumina, losing the water. There are two endothermic peaks. And similarly, this is the TGA results. Again, weight loss, water compared at the same points. And then we took the DTA and DGA of the complex we prepared. And there's a endothermic peak here, a large endothermic peak. And then there is another peak up here. The first one is due to decomposition or deamination, and the second one is due to hydrogen sulfide evolving. And similarly, the TGA results indicate again the two peaks, and the weight loss is consistent, it's stoichiometric. Theoretical is 12.5% weight loss. We observe about 13% weight loss. And now when we synthesize the catalyst on alumina, we have the same peaks that come from both the complex here. This one due to alumina, and this one is again alumina and complex together. Similarly, the PGA peak, PGA results also indicate this is due to the complex. This one is alumina. This one is combined both in alumina and the complex. So we're pretty much convinced that we could put or synthesize the organometallic complex together with alumina in the solid phase at any nickel to molybdenum or the active metal ratio we want. We then proceeded with some physical adsorption data, which were supposed to be followed by IR data, but that supposed to be part didn't work out. So I'll just give the physical adsorption part. We observed practically no carbon monoxide adsorption on the catalyst at room temperature, both on the unused catalyst in activated form and also on the used catalyst. The hydrogen adsorption at 250 degrees, there is hydrogen adsorption on the unused catalyst, but there is no hydrogen adsorption on the used catalyst. And then we did the NO adsorption, and we followed, there's NO adsorption both on the used catalyst, both on the unused catalyst and also on the used catalyst. Now this is a static equilibration technique, and then we proceeded with taking the IR spectra of NO adsorption, and at that stage we were unsuccessful. In fact, I told Dr. Anthony maybe we shouldn't bring that paper because I was hoping to get that data too. But we don't see anything at IR in the range where we should see 3 peaks. Now what that means, I'm open to suggestions. Now the reaction, kernel and denitrogenation, this is the mechanism given by Will Hatcher and his students. Basically, we're looking at quinoline ring hydrogenations followed by nitrogen removal going into a propyl cyclohexane or going through a orthopropylaniline to propylbenzene. And the key components we have identified and looked at are propylbenzene and propyl cyclohexane as the denitrogenated compounds, and all the others as nitrogenated compounds. And we have neglected all the others. That gives us a material balance closure of the order 85 to 90%. And we can identify the nitrogen compounds, but we haven't bothered with the rest of the hydrocarbons. So, the initial start of this catalyst, all test runs were done at 375 degrees, 900 pounds pressure, at space-time 387 hours, gram catalyst per mole quinolane. And the time on stream, the catalyst rapidly deactivates in about 25-30 hours and then reaches steady state activity. And long time on stream, there is no change in the activity. And the way this is really maybe should be called the selectivity, it's the hydrocarbons or denitrogenated products over the nitrogen-containing products. Encouraged with these results, we compare the initial activity of this catalyst with HDN30 at the same conditions, and it looks like the initial activity is significantly higher than a commercial HDN30 catalyst. At the test range, we're about an order of magnitude higher in activity. For product distribution, also on a commercial catalyst, quinolane is rapidly turned into the first hydrogenation compounds, so you never see any quinolane, but basically here we have the propylcyclohexane as the final product, and propylbenzene is here as the final product. And this is the HDN30 catalyst. And at the same conditions, this catalyst gives same type of behavior. Product distribution is similar, except of course due to activity, the denitrogenated products are higher in amount. We then took this catalyst and run it about 430 hours on stream, trying different things. This is the initial startup curve I already showed. And after cooling it down under hydrogen sulfide and starting up again, there always is pretty much a step decline in activity. And it continues again, pretty much steady. This is simply hydrogen sulfide hydrogen treatment, which really doesn't do anything. And then activation by oxygen, followed by pre-sulfiding, again gives us the same type of activity decay, so the catalyst comes back to the almost close to initial activity, and then it starts declining again. And when we look at the four distributions, the unused catalyst is about an average core diameter of about 40 angstroms, surface area of 236 square meters, and used catalyst shows a similar behavior. The average pore size is still the same, area is reduced, indicating probably uniform deactivation or uniform loss in pore volume. And reactivated catalyst again gives the similar sort of single one of dispersed pore distribution at about the same size. So based on these results, I wish I had the IR results as well to show what the species forming are. Based on these results, we conclude that these are mixed sulfides on the surface, and their activity is higher than even commercial catalysts, which are prepared with all the other additives, promoters, and so on. And it looks like this might be one approach of preparing a well-dispersed mixed sulfide catalyst on alumina carrier.